So, hi there. I'm Jordan Fink, currently a PhD student in the Environmental Science graduate program here at OSU. And I'm in maybe the first third of my time. A lot of my work is focused on systems and systems theory, and I've been working in systems in one way or another for 20 odd years. And I was delighted when Carolyn put me in touch with Stephen, and the two of them asked me to talk with you all about systems. You know, the idea of systems is something that we hear a lot about right now. We're at the point where maybe 15 years ago, systems theory seemed really jargony. But now even major corporations are thinking in terms of systems. People are talking about systems. And like any word, it can be overused. So I think it's good for us to get into what are we actually talking about when we're talking about systems. So if I have any goal for the next hour with all of you, it is to get us thinking about what it means to think systemically, to think about why it's important that we look at things systemically, why this concept has taken off in so many different facets of life. We can talk about different kinds of systems. And I also want to talk to you a little bit about some of the pitfalls. So systems are fundamental to the way that we work in environmental science and the way that we work in ecology. And a lot of that had to do with a reinvigoration and reapplication of systems theory to ecology that happened in early 70s, late 60s. And a lot of this had to do with questions that were coming up about things like the Apollo mission. It really was a question that people had. You know, we had never really sent a human being into space before. So I have a friend who is a systems ecologist, soil scientist. And she and her husband and some of their peers, they were soil scientists together, and they focused on ecosystems. Before that, the majority of soil science that was being funded was agronomy, agricultural soils. But there was this window of time where system science was part of her picture. And I was asking her about it. And she said, well, you know, there was all of this interest in the Apollo mission, all this money that was coming from NASA. Because when they were sending a person out into space, they really didn't know what was the environment contributing. How do we account for all the things that a human being needs? What is the nutrition? What is the life support system? What is the effect of gravity? What are all of these elements? And out of that system science, we find ourselves in a world where here we have the technology that is well beyond anything that they used to send somebody to space, and we're able to talk instantaneously if we wanted to. This could be a stream rather than a recording. We also can go to the store and we can buy nutrition. We can have the nutrition evaluated of our food, and all of that is also a product of that legacy of system science that sort of emerged at that time. And there's other veins and other reasons why systems got important. But they all kind of come down to one issue, which is kind of the fundamental issue that we deal with in environmental science. We grew up, a lot of us, with the term environmental. We don't think about what that word actually means, that the environment is all of the things that support and surround a thing. My environment right now is my study. My environment is also Portland, Oregon, where I currently am. My environment are the places that I live. And when we're doing environmental science, well, how's that different than biology? I think it's a fundamental question. How is that different than the study of an individual organism or even the study of an individual interaction? And that's not to say that we can't be reductionist at times. We can't look at the world and take it into parts. But let's talk about systems for a second. So, the other day, my friend was going through a hard time. And he was being really, really hard on himself. And this is, hard to say, but I basically was trying to point that out to him, that he was being too hard on himself and he wasn't hitting him. And I said, well, you're just a big idiot. Now that's an interesting statement, right? If I had just written down the transcript of that conversation, you might think I'm being mean. But what I was doing was I was showing him, hey, that's not real, or that's just a voice that's telling you something. And the reason why that wasn't a damaging part of our friendship is because of the context of our friendship. Within our friendship, I have communicated enough ways and shown enough ways that I'm a safe person. And so the movement of this toxic language, you're an idiot, into something that was playful and pushing is because we knew that we were safe together. And you can't just study a statement. Would be an anthropological question. You can't just study a statement and say, like, what is the characteristic of that communication just through the words. And in the same way, we have the same issues. You might take a wolf out of a pack and study that wolf. You could look at a wolf's skeleton. You could look at the biological systems of the wolf, the internal organs. And what would that tell you about the herd? The herd is the context for the wolf. And in the same way, how can you talk about the wolf without talking about the deer population that the wolves are interacting with? They are descriptions of each other. Same thing with that deer. The deer have ears the way they do, and they have hooves the way they do, and they have behaviors because of the interactions with the wolves, but also the interactions with each other. And a lot of those traits are traits that are there because of things that have never happened to that deer. That deer antlers might be there to protect itself from wolves. And as a baby, as a young, or once they get their first antlers, it's going to be part of these mating rituals, but they're not ready for that yet. So there's all these traits that a community shares systemically, because that wolf knows that it's had to run to catch deer, and that deer knows that it's had to, but it's not the individual wolf, it's not the individual deer, it's the community that they're within. Same thing with the evolution of something like a hand, right? We know that this happened within a context. The holding of branches as primates, the working with stone tools, the picking of berries, the ability and need to be dexterous with it. Our hands are given to us through, our development, through a genetic pool that has gone through all of these different processes. It's systemic. So we can't understand a thing without understanding the environment that it's within. So when we started thinking about systems, we started asking, we'll talk about things like the family system. This is one place where systems have shown up. But we also talk about the system when we talk about the political structure or the cultural structure. When people talk about racism or classism or even academia, these are all systems. And they all have a logic to them. That's something key to systems theory, is that every system has something that it's trying to do. And that purpose, that goal, that process has evolved over time. The famous systems ecologist Howard Odum, who's one of my biggest heroes, was also a mentor of Carolyn's. Howard Odum talked about how the systems that survive in any ecology or any environment or any thermodynamic system are the ones that have the ability to take some of the information, materials, and energy. Those are the big three: materials, energy, information. They're going to take some of that which they receive, and they're going to put it back towards securing them. So that wolf eats the deer, gets the energy, uses some of it to take care of its body, to take care of its social relationships, but then it also has to make sure that it takes some of it back towards hunting. And the deer is the same thing. Their relationships back to the woodlands, to the shrubs, to the oaks that are growing up underneath the mother oaks. Those relationships are happening in the same way. That systems survive that are interacting and supporting the systems that support them. So we talk about these different kinds of structures, these different kinds of systems. And as environmentalists, it's essential that we talk about it this way, right? Otherwise, you have the danger of trying to understand the part. Now, understanding the part is important. When I look at the system of a car or a system of a bicycle, I need to know that the chain is strong. I need to look at my chain of my bicycle and clean it and make sure that it's functioning. I need to look at the spokes. I need to attend to the tire. But the bicycle itself is a system, and it's also a system with me, my awareness, my moving of the bicycle, my repair of the bicycle's tendencies, the bicycle's reactions to the ground, my reactions to the bicycle's reactions to the ground. All these things are happening at once. So let's imagine the simplest system that I can even think of, which is I'm in my shower and I'm adjusting two knobs. I've got two knobs in front of me. One's the cold, one's the hot. And some knobs are a little different too. There's ones that are the cold and hot is one knob, and the other one is just the amount of water. And there's a really cool graphic that I think I'm going to attach to the homework that shows a graphic of the same system just viewed with those two different types of control structures. But here's a system. You're in the shower. The water's a little too cold. You adjust the knobs until it gets a little warmer. Well, maybe now it's getting a little too warm, and you adjust the knobs so it gets a little colder. And so you and the faucet are interacting with each other. This is what's called a negative feedback system. One of them has a tendency to get off the rails, and the other one has the tendency to try to stabilize it, me. So me and my shower, we constitute a system with each other, and between us there's interactions. You can get more complicated with that. Systems have settings, but with that shower, for example, over time the amount of hot water is going to decrease, and I'm going to have to start adjusting. I'm going to have to start turning up the heat of the thing to adjust. And there is some point at which the temperature that's coming in and the amount of temperature that's my tolerances, they're going to cross each other, and finally I have to get out of the shower. But again, systems have their limits. So these kinds of behaviors of positive feedbacks and negative feedbacks, I want to get the language of that right. So positive feedbacks, we often talk about this differently than we talk about culturally. So if I were to give you positive feedback, it would be like, well, hey, I really like your jacket. And negative feedback would be like, I didn't appreciate the way you said that. Well, in systems ecology, we actually mean different things when we talk about positive and negative feedback. So when we talk about positive feedbacks, we're talking about things that escalate, that run away. Oh, and an example of that might be that you are in a conflict relationship with someone. You and somebody are in a little bit of conflict, and you do something small that bugs them, and they do something that bugs you, and you say something that escalates, and the conflict escalates over time. The cyberneticists called this schismogenesis, the process by which amplification and runaway happens between components in a system. And this is something that can happen. We can have escalations where we're going to talk later about a model of fisheries. And we can talk about a system where how does that run away? If the fish get more scarce, do people fish more or do they fish less? So negative feedback would be a system where the less fish there are, the less fishing that happens, and the fish can return, and then the people return, and the fish. So there's this balance. But the alternative is that there's a runaway process, that a thing causes a thing causes a thing. We're seeing that in climate models now where, carbon being burnt reaches a threshold, which now puts out methane, which puts up water vapor, which then heats up things, which then puts methane. And this is that vicious cycle. These are positive feedback loops. And a positive feedback loop could happen if I put the speakers of this recording out and it gets louder and louder until it's screeching. That's a positive feedback loop. Now, negative feedback loops actually aren't negative in a cultural sense. They're negative in that they're stabilizing. So a robotic car, or you in a car, let's just stick with humans, you in your car, or me and my bicycle, I have a goal of stability, and I have a goal of a destination. And so as the bicycle moves one way, I rock the other way. And as the bicycle rocks the other way, I rock the other way. And we together constitute a system. By itself, the bicycle would fall. By myself, I would be in the air and I'd fall over, or I wouldn't be moving as fast. But together, we make and constitute a system that is having this negative feedback, this stabilization. So there are all sorts of kinds of feedbacks that are happening. This is something you can't tell from the parts. So I want to teach you a little bit. At the end of this, I'm going to have you all think about something in your life that is systemic. And I'm going to say systems theory, it can cover a lot of types of systems. So we could be talking about an organization. We could be talking about an organization that interacts with an environment. We could be talking about systems within the environment. We could be talking about an animal and its community or its needs. We could be talking about the political economy and the role of information acquisition and its effects on how behavior happens in a system. So, wherever you're coming from right now, there are systems that you're interested in. Some of you are in the business degree and you're interested in environmentalism, environment and business and the relationships with that. The question, can business work in a way that actually helps the environment? Can businesses help in a way that actually supports the environment? I don't know. This is our job. Some of us are studying individual animals. Maybe we're looking at condors and like why their niche is falling apart and how to improve it. Or we're looking at salmon ecology and we're trying to understand what's going on there. And what we're doing when we think systemically is we're building models. And I'm going to say another axiom here, which is that all models are wrong, right? We build our models and they're wrong. And there is a question about like, how do we build models that are close enough that we can be adaptive with them? And so what I'm about to show you is a way of starting to think through the making of models. And your assignment is going to be to start drawing and exploring a system. So maybe in the back of your mind right now, you can think about a system that you're interested in. Like I said, a community, a family, a conflict, a war zone, a community that is on the edge or precipice of conflict but hasn't gotten there yet, a plant community, a system that's oscillating between being eutrophic water and oxygenated water. All of these are totally appropriate. So don't feel overwhelmed. Pick something that you're curious about. And what I'm going to explore with you is how do we start drawing this out? One of the great things about the work of Howard T. Odum, he's one of my heroes, is that he came into systems ecology with his brother Eugene with a background in electrical engineering. And what that let him do, electrical engineers are dealing with really complicated systems of different kinds of processes, and they've learned to take the equations of those systems and draw them as diagrams. And so Howard Odum took this idea and said, okay, we're going to make a visual language for the description of complex systems. And behind the scenes, if you look under the hood, you can build equations that actually follow that. We're not going to build equations, but just to let you know, these drawings actually represent differential equations, and we can from there start to build systems models on computers that follow this. So I'm going to switch screens so that we can talk a little bit while I draw. Yeah, here we go. So here's what I want to explore first. We're gonna make up a couple different kinds of systems together, and I'm going to use some nomenclature. So let's start with a couple things. One is all systems have some kind of boundary. So I need to make sure that I'm doing this so that the screen matches where we want. All right. So all systems have some kind of boundary. Oh, that did not work correctly. Give me a second. So all systems have some kind of boundary. Now, the thing I want to say about this idea of a system boundary is that it's artificial. You know, if we're going to model the system of a human body, you could imagine your skin is your boundary, but the truth is your skin is an interface. So what I like to say, and this comes from the works of Gregory and Nora Bateson, father and daughter, is that what a boundary is it's an interface. It's an interface for mutual learning. Right? It's an interface. But at the same time, if I'm going to be modeling water in a water basin, I might as well draw the ridges of that basin as this edge of my boundary, because at some point I'm just going to have to talk about it. But every system has inputs. So I'm going to tell you on the global level, there are three main inputs. And we like to draw these as circles. This is just sort of the nomenclature. And in this case, the main inputs into the biosphere, the geobiosphere, are the sun. There's a lot of solar energy that has gone in over long periods of time. There's the geology, and there's actually huge amounts of geothermal energy, both the gravitational energy of the Earth itself, the process of magma and plate movement, and the energy that's inherent in that system. And there's also nuclear decay. Under those pressures and those heats, there is the release of energy from the isotopes as they go through decay. And so geo represents the second, and then the third is lunar. And lunar energy is doing all sorts of pulling on the water and the air and the materials of the Earth. It's squeezing and squishing it, and its tidal forces are actually rather significant. So we like to say in systems ecology that these are the global baseline. And you can put numbers to these. You can say how much energy is coming in from the sun, how much is due to geothermal, and how much is due to lunar. And if you want more information on the current status of that, this is always being discussed among folks in the world of emergy. I'm going to write this out, so it's EM, emergy, which is the study of all of the total systems of energy that go into something. We'll talk about that a little bit. But this question of the global baseline. So, okay, the system has inputs: sunlight, geo, lunar. In that, though, there's a couple things going on. There are, of course, I'm not even going to talk about in this case, we're talking about the biological parts of a system. So there are the plants. Now we use this symbol to talk about plants, and we use that because it looks like it's receiving something. So we just have plants. And this could include many different kinds of plants. But we can also flatten it and just say plants in general. And maybe these are shrubs. Maybe these are grasses. Maybe we'll even have trees. And in this case, I'm going to have them eaten, like I said before, by a deer. So there we go. Plants, energy goes into these plants. The plants are absorbing geo energy, all those minerals. They're affected by water systems. So we might actually say that there's a number of systems outside of this. There's also water. And water here we're putting as a little tank symbol. So this is the symbol we use for storages. So in this case, the water gets its energy also from the sun, because we know that water is salty in the oceans and the sunlight lifts it up, carries it over in the air, drops it down on the landscape. And that's held, that solar energy is held in the water in the form of its cleanliness, which allows it to do chemical potential work, and in terms of its elevation, which is what allows it to do mechanical work, which allows it to carve rivers, carve landscapes. But for whatever reason, the water now has helped the plants. And I'm going to clear this up a little bit. We're going to simplify this system a little bit. We've acknowledged that there's many different kinds of plants. So I'm just going to simplify our system. In fact, I might just simplify our system to the point where we're just looking at the plants, the deer, and wolves. Here we go. So plants, in order to build themselves, they have to use a lot of internal energy. They're actually having to maintain their lives. They're having to reproduce themselves. And they're trying to grow in population. The deer are also trying to do the same thing. They're putting a lot of their energy towards their own maintenance. The wolves as well are also working on doing their wolf things. There's lots of behavior, lots of interactions, lots of things that they have to do, lots of things they have to navigate. And in order to do work in natural systems, we have to account for entropy. This is basic thermodynamics. And so we put a sink. And all this means is, for all of the energy of sunlight that goes into the plants, only some of that sunlight is actually in the plants themselves. But when you look at the plants, you can see that it took all this sunlight and all this energy and all this heat and all this process to build the plant, but a lot of it's not present anymore. That had to go down the drain, become heat, become evapotranspiration, become something else. But there's a difference. And in the same way, the deer had to eat a lot more plants than deer, and the wolves had to eat a lot more deer than wolves. That's one of the reasons why we end up seeing ecologies that have trophic pyramids, where we might have plants at the bottom, deer in the middle, wolves on the top. And we notice that the amount of wolves is smaller. Maybe a tenth is a good average, good rough average. A tenth of the amount of biomass of wolves to the amount of deer, and a tenth of the amount of deer to the amount of plants. And there's a reason for this. Each one supports the next in the trophic hierarchy. So, plants, deers, and wolves. Now, let's close down this system, and let's put it all within one window. And let's take all of this and shrink it down. And recognize that there's an environment of all sorts of interactions happening. These are just examples of these trophic pyramids that are happening. But let's just say that this is the environment. For us, our environment. And so, out of that's supporting a human population. People. And people are also doing all sorts of things to secure their resources. And they're having all sorts of interactions with the environment. And people themselves are producing information and systems of people. So we have the economy. And the economy is interacting with people. The economy is interacting with the environment. The economy is drawing from the environment. And all of these, of course, have losses that have to happen. This is just basic thermodynamics, that systems, in order for them to work, have to have some losses. So the economy also has a different kind of information system. And in this case, we're going to talk about the fact that in order to interact with the economy, people receive goods from the economy and they pay money. So here is a financial process, and people put labor into the economy and they give back. So there's a loop there of people, the economy, and money is transferred. And there's a rate that's been set here of a relationship between the money and the exchange, and the money and the labor. There's a rate. So I want to talk now about a case study. We can do all sorts of things while we explore this. So what I want to imagine is a very famous example. This is called maximum sustained yield. MSY, maximum sustained yield. And this is a question that started to come up in the 70s, which is, we know that organisms might grow fast, slow at first, fast, and then they reach a carrying capacity, and they slow down in growth rate again. And this is what we think of as the carrying capacity. And they do that because here down in the middle, lots of opportunities for food, lots of room. And here at the top, a little bit more competition. And a sustainable population of fish is going to have this balance point that it finds, where it has enough of one kind of resource or it has enough of another. Okay, so imagine you have a system. You have a pond or a lake. And around that pond, you've got all these fish that are growing. And the fish population has a relationship. It has a carrying capacity. Well, a bunch of people move in next to it and they start harvesting fish. And it turns out that there is an economy that allows them to sell those fish if people buy the fish. So these are fishermen, and these are consumers. So the consumers, the pond grows the fish are fished by the people, and the consumers eat the fish. Well, we know that there's this money flow that's happening between the consumers and the fisher people. And we know that there's all sorts of backflows of behavior that are happening between the fishermen and the fish. And we know that the fish is having interactions with its environment in the pond. So the question is, what is maximum sustained yield? So maximum sustained yield is this idea that because of the growth rate of fish, if you harvest up to a certain amount, you keep the fish in this mid-range. And in this mid-range, there will be a replenishment. We know that if we harvest more than that amount, that the fish population will go into a recovery mode, and it will, have more room, and it'll grow back. But if you overharvest, there's a point at which you'll cause a crash. So maximum sustained yield is this idea of sustainability. It's actually where a lot of the language of sustainability comes from. A sustainable society would be one that takes less than the replenishment rate of the things that it takes. And it'd be one that only pollutes or only creates waste products that are processable by the system that they're in. But there's something else here that doesn't necessarily always get talked about, and I really appreciate Donella Meadows, who's really like one of the main mothers of systems theory. Donella Meadows made the limits to growth study that was done in 1970 by the Club of Rome that really looked at limits to growth and potential crises that we might be facing now in the 2020s. Important work, and unfortunately dead on in terms of some of the descriptions of hitting peak oil, peak fuels, peak phosphorus, also maybe even peak information and peak access to healthcare. There's all these sort of limits that happen and that have to be sort of attended to. So imagine this scenario. Our hope here is that there's something that's going to happen that as the fish population goes up, and the human amount of fishing will go down. So in the theoretical system here, the people harvest the fish, and they have to buy boats to catch the fish. The fish have to be able to have a price point that people can afford. If the price goes up, people aren't going to buy as much fish. And you buy more boats, you invest in your fishery. The price is still worth it. It's still worth it. You harvest. And then as the fish population starts to decline, it gets harder to catch fish. It gets more expensive. It isn't worth it investing in more boats. You have to charge more for the fish. The people buy less fish, and the system stabilizes again. This is what we're really trying to go for when we talk about sustainable development goals or global sustainability goals or dealing with the limits to growth. Now, Donella Meadows, there's two things going on that we need to talk about that are I've oversimplified. And one of them is sitting over here. It's in the pond. There's all sorts of processes that are happening that are not being measured because the people here are doing a measurement. They're observing the fish population, and they're hoping, and they're observing the economy, and they're trying to get the price points right. Some of that happens naturally, some of that happens automatically, but some of it happens through good planning. But there's all sorts of things contributing, and many of them we don't even know what they are. For example, we may not know that the other fish, the ones that we don't think about as much, or the things that the fish eat. We might not know the importance of the edge of the bank and the way that it handles water, or the way that silt is processed, or something as simple as having enough willow trees around the edges of the pond so that the willow trees contribute butyric acid, which contributes to the microbes that get into the waterway so that they support oxygenation in the environment rather than allowing things to get eutrophic and deadly toxic. So all these things are sort of happening in the background, and our sustainable goals, it's really hard to track all of that. We may not be aware of all the things that are actually engaging and happening, but we can look at fish and we can look at how much there are, and we can try to adjust. And there's something else going on here, which is Something about the consumers. There's an assumption here that the consumers have a normal distribution of wealth. There's kind of like an average consumer's wealth. And as you go up, there's richer people and there's poorer people. And in this model, this is just the model, this is saying that there actually is a price at which fish start getting a little too expensive. People stop buying tuna as they get more and more pricey, or stop buying trout, or whatever it is, And we know that the economy is not organized this way. The economy is actually much more like this, depending on the way you look at it. If this is like wealth, actually, no, I'm sorry, it's the opposite. It would be like this. It obeys what's called a power law. And what that means is, we get to a certain price point and the vast majority cannot afford that fish, but there's always someone who can, no matter what the price point is. So as Donella Meadows said, if you don't have some degree of a normal distribution in your economy, you're going to end up with a situation where someone can always buy the last tuna. So there's the first problem. The first is that this is actually potentially an escalating environment. That if you have unequal access, unequal money, financial resources, the controls might not be there. This might actually become a positive feedback loop. And this might become a positive feedback loop. And this might become a positive feedback loop. And the fish population crashes. So, okay, we build legal systems, we build protections, we put, for the ones that are really hitting the edge, we have endangered species laws. And, we keep trying to add new layers of control to this system. And there's something else happening too. So for a long time, this is sort of like how we talked about sustainability, how we talked about systems. We build the model, we get the parts, we look at how they're interacting with each other. And in this, I could be adding things like the willow trees. And I could be adding the microbes. And I can be adding the other organisms other than the fish. There's so many different organisms that might be having some kind of relationship. And we could start drawing all of them out. And they all have interactions with each other. And some of those interactions are completely out of sight. Well, C.S. Holling in the early 70s wrote this pinnacle paper where he was looking at actual examples of fisheries that supposedly you look at the populations and everything's going fine. Prices are responding correctly, harvests are responding correctly, fish population goes up, price goes up, or price goes down, fish population starts to go down, price goes up, things are balanced. But then you'd see a sudden a break would happen and the system would fall apart and the entire waterway would go eutrophic. Lose its oxygen, and it would be an irreversible or very, very difficult, very expensive to reverse system, the collapse of a fishery. And he started to ask, well, why is that happening? And we can come up with hypotheses for why it's happening, but all of those hypotheses involve trying to bring in more outside information. Maybe the amount of willow trees goes down because of compaction, or because of, as we get more boats, we're trying to get more access. Maybe there's a process in the food web that we're not aware of. Maybe reaching peak distribution of fish is actually an important state that has all sorts of processes that happen in the water, and that having fish oscillating up here well above the maximum sustained yield allows for population dynamics that one wouldn't have imagined, one would not have theorized. And the other alternative approach to that is that we might not be aware of the importance of a boom and bust. Some systems do go through ups and downs. Maybe the fish population wasn't as stable as we thought, or maybe the rules aren't as stable as we thought, or maybe something else has changed. Maybe there's a change in phosphorus in the water. Maybe there's a change in the climatic cycle. Maybe there's a change in the behavior of the fish themselves when they've been kept in this mid-succession phase. We don't know. And so that becomes a very big question to ask when we're looking at these kinds of systems. We may not know all of the states. So he started to identify what he called resilience, which is the model of a system that actually, as we start to control sustainability, we may actually accidentally be declining in resilience. The brittleness of the system may increase itself. So it can be very difficult to get more information. again, the model is not the terrain. The situation is not, what it really is. But these are important questions to be asking when we're modeling any kind of ecology, when we're thinking about any of that stuff. So this is just one example of exploring systems processes and how these pieces work. We can also talk about the fact that we may use this as an opportunity to explore all of the different ways that something might change in an ecology, or even like what all of the pieces are in a puzzle. Donella Meadows used to say that when she would go and consult with businesses or organizations or agencies, people actually had a pretty good instinct for where the leverage points in systems are. But she found that they often pushed the wrong way on those levers, on those processes. And there's a great reading that I'm going to have you read that explores some of these questions about points to intervene in a system. If we're going to be involved in systems, how do we intervene in them in ways that are helpful? It's really important to be thinking about things this way. And part of it is because we can't really know the individual character. So another example I want to give, another aquatic example is here in the Pacific Northwest, we have, forested mountains. Sorry for my drawings, but I'm just gonna make little iconic drawings. We have these forests, and we have river systems, and we have a big ocean ecology full of phytoplankton and all these microbes that are collecting diffusely. And we have salmon. And those salmon come up from the ocean. They go into the rivers. They come up to the rivers where they're born. They dig redds. They actually go in there and they clean out the riffles so that there isn't silt and so oxygen can move up through them. They lay their eggs, and the babies go out to the ocean and for a long cycle live out into the ocean eating, and then they come back home and repeat the cycle. And we know that when we look at the forest, we see the salmon because we can actually look at the thickness of tree rings and see that it's related to the intensity of the salmon population of that year. So salmon bring all this ocean nutrient that's washing out back up, and the salmon have an interaction. I don't have a good brown color ready to go, but they have an interaction with the beavers. This is my beaver. And the beavers are modifying the streams so that they are braided and so they're, a certain kind of pattern. And that happens to enhance the salmon. Well, the salmon are also being eaten by birds and birds of prey. I'm not going to draw a quick bird, but by birds and by bears. And those animals are distributing the salmon, and it's controlling their behavior and their interactions with the forest. And the salmon are moving out all their biology, all that food after they're spent. After they've taken care of themselves, they take care of the forest, and the forests take care of the rivers, and the rivers take. The cycle happens. And we could draw this, right? We could say we have ocean phytoplankton, and plankton in general, and we have the salmon, and maybe we have the salmon's interactions with the river happening. The river and the salmon are influencing each other. The phytoplankton and the salmon are influencing each other. And the salmon and the bears are influencing each other. And the bears and the salmon are influencing the trees. And the trees are influencing the river. And the trees are also holding back nutrients. So they're protecting the ocean from the erosion in those patterns. So this system was starting to go into decline, right? We overfished, we cut down a huge amount of the forests, we built dams for hydro, we redirected some of that water energy for human purposes, so the human elements here. And so, wait, I'm going to say something first, which is All of this system also, though, grew up, found itself. When the ice ages were here, they weren't salmon weren't present in Washington state. They were was all under glaciers. But we know that human populations, indigenous populations, were here at that time. We have now records back. So as the glaciers retreated, people were there. And so as salmon came in, people have been part of this process too. So people harvest the salmon and they take care of the trees and they benefit from the trees and they interact with the rivers and the rivers interact with them. And there's a human component in it too. Well, we had a massive genocide and a switch over to a different colonial model and a different group of people in an extractive process of tree harvesting. And then also later, a practice of tree harvesting that is hopefully more sustainable and more like modern forestry. But we also know that when San Francisco burnt down in the big fire, when the earthquakes hit San Francisco, turn of the century, the trees around Lake Washington were the trees that were harvested. The giant old growth were harvested and became the city of San Francisco. So big changes in the salmon population, big changes in the communities, big changes in the fisheries. And now salmon reach a point where their populations are low enough that EPA money starts showing up in the 80s and 90s. So there becomes an institutional level where now the Endangered Species Act is involved. And the Endangered Species Act hires people and puts money into rivers. And there was a massive boom in river restoration and a massive re-education of engineers, biologists, planners, all of these people, the whole world of amazing salmon restoration and river restoration. And there was a period of time, though, where the money itself was happening and it was meant to create reference reaches. So Matt Condolf, who's a river restoration professor down at UC Berkeley, he wrote this paper saying, looks like the first wave of rivers where we just sort of like asked the question, what does a coho need? We just looked at a coho and we said, which is a kind of salmon if you don't know, and we said, well, what does it need? Well, it has all of these inputs. It has all of these qualities of its environment. It has all of these river spaces. It has all of these kinds of structures that it needs. And we created essentially rivers that were just coho hotels, just coho habitat. And you saw some boom bust coho population stuff happening. And in some places, maybe even that boom bust is improving over time. Maybe there's other factors over time that are making it worse. Depends on the river system. And maybe there's chaotic effects that we don't even understand if we look at the coho population over time. But one thing he pointed out was that there were a huge number of fish that were not considered. That the river itself was not just designed for coho, but they had carved rivers and put in wood and shaped it so that the dynamics of the water would create optimum coho nesting habitat, and that they would build structures and patterns and mathematics and build their models around the coho. So again, we have this problem of like trying to maximize one aspect of the system through our system analysis and realizing there are invisible parts. So building a full ecology, what does that look like? Now, things can't be restored back to what they were. They're always changing. There's always new dynamics. There's new species. There's loss of species. We're dealing with massive climate change. So how do we talk about stability? How do we talk about working together? How do we talk about feedbacks? How do we talk about priorities and navigation? And one of the ways that these systems work, and I'm gonna move out of the drawing. Well, maybe I'll stay in the drawing for now. One of the ways these systems work is that they back each other. If you think about a meadow, there are all sorts of pollinators. There's all sorts, just even in my yard, I started building a meadow in my yard, and I saw over 30 different types of pollinators of different types, from little parasitic wasps to that have interactions of many different types to different kinds of bees, different types of flies, butterflies, birds, bats. Like there's this whole thing, and there's many different kinds of plants, and In my garden, I made sure that there were always flowers at any time during the growing season because I knew that I wanted to make sure that somebody was around. And I also tried to make sure there's diversity. Well, the reason we care about diversity in ecosystems is that in a system that survives, there's lots of parts and they aren't always stable. And somebody covers for the others. One steps in. So as we start to narrow systems and narrow options, we may find ourselves working towards a stability that is actually a dead end. We have to recognize that I have never run from a bear, but my ancestors have at some point. And there is in me all sorts of biological knowledge that is there because of the experiences of others. The same thing's true for a plant community. We don't know all of the different ecological ranges. For example, Doug fir trees in Oregon right now, if you plant if there's one big Doug fir above a clear cut, you're going to see a stand of Doug fir. And if you head all the way down to Sierra Nevada, they still have Doug firs, but every year Doug firs drop their cones and there's no babies. It's just too dry. And I was talking with somebody, actually, no, I was reading the poet Gary Snyder, who's lived there for years. And he said, every 50 years or so, there's a wet July. And so there might be one or two trees that make it. So the same species, the same organism, the Douglas fir, has an entirely different life cycle in the Pacific Northwest and in the Sierra Nevada. And side note, climate models are suggesting that we're going to have an ecology very similar to the Sierra Nevada within the next 50 years or so, convergent models. So even the species around us right now, they have a range of behaviors. They have a range of approaches because their characteristics are not just innate in the thing, they're systemic. They're in that system. So I hope I've gotten you thinking a little bit about this idea of the necessity of thinking systemically, of thinking in groups, in thinking of relationships, the difficulties of doing it, that we have to be playing with it all the time. But there's things that we can't do without thinking about things in context or thinking about things in relationships to each other. The question is, do systems remember crises? Forests remembering the forest fires that have come through. There's species that know how to do the recovery. Species that know how to fill in a gap in the forest. Species that wait. I grow chestnut trees at home, and the chestnut trees are fine in the shade, but they stay small, and they're waiting for a hole in the canopy, and then they grow huge really fast up through that hole. So this question of how does this work? How do we interact with each other? And frankly, we're getting very, very good with computing at modeling systems and modeling control. So the thing I want to leave you with last is we're living in a world now where we're able to get pretty real-time monitoring, and a lot of people have made this leap to the mathematics of it and this idea that, well, if we have a perfect model, we can interact with the model and we can steer really quickly. A lot of AI, a lot of this tech work that we're doing, right, is that we have these models and we see as the system starts to deviate from the model, and then we can take the corrective action, assuming we know what the corrective action is. And it's not a big jump from controlling a very simple steering system to thinking that you can control the whole thing. But something I'd like to say is that in all systems, anything that we imagine as stability is really because everything else is moving. If you've ever gone through a period of your life where you've gone through a big change in your friend group, like a change in who you are, people kind of they navigate you. They change their relationships with you. They learn who you are. They adjust, they adapt. There's less wolves, or there's less deer in the forest, and the wolves come in a different way and start hunting something else. Coyotes behave differently, as they get bigger because of the dynamics as they move into the eastern forests. There are shifts and changes. And a meadow keeps meadowing, keeps being a meadow, even as it's different flowers and different processes and different years and wet years and dry years. So how do we make sure that we aren't pretending that our models are reality, even though we can use these models to explore. So that's my question to you. And we've talked about a lot of different things, but I think it would be pretty cool to see what you come up with. You know, I could draw a diagram of my family. Right now, my family is, I'm an only child. I have two parents. They're aging. Their behaviors are changing. They're not as mobile. My dad just had heart failure, and it's changing the way that my mom and my dad are interacting. And they're having to interact with bureaucratic systems and surgeries. And, my dad's interacting with the VA because he was a vet. And that's changing interactions with their family back in the Midwest that I didn't know very much. So now I'm on the phone all the time with my dad's sisters and my mom's family. And all of these changes are happening in our family. And at the same time, that's affecting me. It's affecting school. It's affecting the projects I'm involved in. And so it's all at play when we're thinking about systems. So I could model that. I could actually look and see, like, oh, the roles are shifting. Oh, I have different responsibilities than I had before. Oh, the ways we communicate with each other are different. And I'm going to say the family as an example of a system, but this is true of a business. This is true of an organization. This is true of a forest or a biosphere or a planet or a solar system. And the question is one that I think is a really important one. And I've given you a reading with Nora Bateson. I really love some of her work. She uses vocabulary that she likes to make up words. I suggest reading her work with just an open mind to new words, new word making. Here, I'll switch to the main camera for the end of this. And her question, I think it's a good one, is where's the family? Is it in the individuals? You could take apart a person and you wouldn't find the family. No, my mom's in my heart and my cousins are in my heart, but like the family's not in me because it's also in them. So then you could say, okay, we're circles and there's arrows between us, and those represent moments, exchanges, kindnesses, communications, conflicts, like all of the different kinds of interactions that we have with each other, gifts, silences, the non-interaction, the non-communications. So is the family must then be in that, right? In the interactions. But my family now and my family a long time ago had a different set of interactions. So there are things and interactions that are possible. So maybe the family is in the set of interactions that are possible rather than in the interactions. The same thing's true for a meadow. The meadow is everything's living and dying at different rates and different speeds and different compositions and different moments, and there's different water flows and there's so much change. So it's in the interactions. But not everything's possible in a meadow. Not every interaction is possible. So it's in the set of possibilities of interactions. So that's something I want to leave you with when you're exploring, when you're drawing out your system. And the homework's real simple. Find something that you want to explore. Start looking at what some of the elements are. Draw them as circles. Draw arrows between them. Explore how things move between them. There's no right way to do this. There's no wrong way to do this. I'm asking you to think creatively. The nice thing about this kind of diagram is that it can be quantified and turned into quantitative models, but it also allows us to be playful. So before I ever build a model, I spend time just playing with drawing things out. And then what I want you to do, and here I'm going to actually pull up the homework itself so that I make sure I am correctly saying it, is I want you to select an environmental system to analyze: a watershed, a forest, a family, a town, organization, a renewable energy system, and create a diagram illustrating these components and the interactions between them, and get crazy. There could be things that you wouldn't even think of. Things to think about: boundaries, storages, centers and flows, interactions and recombinations. Go a little bit more into that. And then from this, I'd like you to write a page or two. Be as brief, be as succinct, be as poetic. I don't have a standard here of, other than that I'd like you to maybe answer some of these questions. So why did you select the specific components and interactions? What are they? Describe. Give me a description. Why'd you pick it? Describe your initial observations on these interactions and any discoveries made during that diagramming process. And then I want you to imagine something going wrong. Climate change, a war breaks out, a storm happens, and there's not enough, cooking oil. Maybe a fire comes through. Maybe there's a drought that lasts for 7 years in what normally is a replenished water supply. Something happens, a stress, there's an earthquake, there's an economic crisis, just something. Your brain is going to be able to think of something that can go wrong with this system. And so now that you have the systems view of it, I want to ask you, how might the system change under the stressor? Like, how do the components and interactions change? How do the sets of interactions change? How does the system respond to and adapt to that event? Maybe the system can actually handle it. That forest fire in a fire-adapted landscape can handle the fire that comes through every 10, 20 years, 50 years, depending on the system. What are the system's vulnerabilities and what are their redundancies? And how does your system diagram assist in modeling potential responses? So right here at the end, it'll help you explore the interconnectedness and resilience of environmental systems using systems theory concepts to deepen your understanding of complex ecological dynamics. This is something very dear to my heart. It can be very intellectual. It can be very theory heavy. But Gregory Bateson used to say that when you really get this stuff, it's in your bones, it's in your elbows, it's in your body. We are in relationships and things are contextual. And systems science is a way of trying to take our reductionist approach, which is important, but also to recognize that it's happening within a context and within a larger story. So I'm thrilled to be able to spend this time with all of you. I'm very curious about the work, and it's been a pleasure to be here and to communicate with all of you. You are all absolutely welcome to reach out to me, especially during this assignment, and ask me questions. I'll put my contact in the assignment. And I think you should have fun with this. Think of it as play. You're safe. You're safe to put in things. There's no wrong answers here. But I would encourage you to spend some time with it and actually give it a go. It's a little bit more advanced than mind mapping, and it's always an interesting way to kind of like explore. It might also be interesting to ask some other people what they would add. So good luck with all of this. It's a pleasure and an honor to speak with all of you, and I want to thank Steve and Carolyn for the opportunity. And I also want to say what an honor it is to be a classmate of all of yours, because I am a PhD student, so I'm in the program as well. I hope everybody's having a good day and that this was an enjoyable experience for you. All right. Thank you.